surface of a material on which the electric field wave with the wave vector k is falling. And if this is taken away, so if this is happening, then we can solve our equation, and this is its solution. So as you see, the electric field decays exponentially going into the material, and decay is governed by this complex part, by the imaginary part of the wave vector k, that exactly what we call a skin depth. If I have that result, then I can calculate what is the intensity of electric current inside of the material, and that is just the integral from 0 to infinity of electric current. So if I use the Ohm law, I can calculate easily that integral, and then the electric current in a medium is proportional to this coefficients E0 and, of course, sigma, but it is divided by the quantity k. And therefore, I can now reverse this calculation, and I can calculate the coefficient E0 and relate it to the current which is flowing into the material. And this relation can be easily rewritten in the way I have written that on the view graph. And the coefficients which appears there are identified as a surface resistivity. That is why it's called R with sub S, and the surface impedance, which I denote by M of S. So the very simple application of a Maxwell equation tells us that if I have an electromagnetic wave, electric field, which gets to the surface of a material which has a certain conductivity, then the electric field gets into the material on a tiny little length, which is denoted by delta. And that is, of course, consistent with our previous discussion of the boundary conditions for electric field. Remember that we said that there is a very peculiar boundary condition on the surface of a medium which has infinite conductivity. Well, because of a definition of delta, we see that this length goes to 0. The penetration and the skin depth goes to 0 when the conductivity increases. So then the electric field does not penetrate a metal surface if this metal is defined as a substance which has the infinite conductivity. Okay, so there is another simple calculation of how much energy is in the little skin, and that is a very simple calculation. If I have a surface and I draw the volume which has a surface A and the length L, then I can calculate the total energy dissipation in that volume, and it is proportional to the square of the electric current and inversely proportional to the sigma. If the field we are discussing, electric field, has the sinusoidal time oscillation, then I can calculate the average value of the energy loss over in this signal. And since the average value of a square of a sine is equal to 1/2, then explain why in this average equation there is a factor 2 different than in the first equation. So I can calculate the total energy loss, and it is again proportional to the delta. So as you see, for the oscillating field, the electromagnetic field, is only getting into the medium in the very thin layer that is...
We can't see the presentation.
Oh, I'm sorry. And that is what we are seeing. So this, now this simple calculation, I mean a very simple property of a Maxwell equation explains why there is a better way of sending electric signals via a bunch of thin wires than via one very thick wire. Because if I have a one very thick wire, the skin depth, thickness over which the electric current only can propagate is the same as for a very thin wire. But if I make lots of thin wires, bundle of thin wires, then the surface area is much larger than in one thick wire, and that is why the normal electricity wires are consisting of a bunch of tiny little copper wires rather than one very thick wire. That is differently when we try to send the DC current. Then for DC current, the situation is different. So with having now this concept in mind, let's discuss that we are coming back to this discussion of a transmission line. And that is a picture of a transmission line, which is one of the very few in the world 500 kilovolts electric lines. I don't have the picture of the similar line which is in Poland. There is one line of that sort which is on the south of Poland, next to the town of Rzeszów. It goes into Ukraine, and that was one of the 5 kilovolts lines which was supposed to be built as a backbone for the electric system of the previous Russian Empire before 89. But there is a piece of that line. That is, of course, a tremendous engineering problem to build that kind of lines. One of the problems is, for example, to have the kind of a safety built in it. What happens if you have a 500 kilovolts line hanging somewhere and something happens? How do you prevent the shortcuts in such lines? And as far as I know, there is only one company in the world which makes the safety switches for such a high voltage. It's Siemens, and these are incredible devices. They are huge pieces of copper. We consider like a Y letter, which move away and when something happens. And in order to prevent the sparks in these devices, they are sealed and they are filled with freon. So the Siemens company had to apply for a permission to be permitted to use a freon. As you know, there's international ban on using the freon, and there are very few industries which are permitted to use the freons. For example, fire extinguishers in airplanes are still using freon, and also the Siemens uses lots of freon for these high voltage switches. Okay. The transmission lines were very important for building the electricity-based civilization, and we, last time I was talking about the Karl Proteus Steinmetz, who was one of the founding fathers of our electric era, and this is also, this is a time to mention another name, is the name of Oliver Heaviside, who was a kind of a forgotten genius of the 19th century. He is author of this famous statement that mathematics is an experimental science and definitions do not come first by later on. And actually Heaviside was a man who had, he was born in a poor family. He got very elementary education. He never went to any university. He even didn't went to something which we will call now lycée. And the way how he survived was that his aunt, husband was a famous engineer, Whetstone, who built the Whetstone Bridge, the resistivity device, and also was one of the first developers of the telegraph in United Kingdom. So he employed Heaviside as a telegrapher in one of his businesses, and in those businesses Heaviside learned by himself all the necessary mathematics, and because at that time Maxwell equations were extremely complicated, because there was 20 equations written in the coordinates, and Heaviside was not very good in handling such an enormous mass of arithmetics. He invented the vector calculus. So the form of the Maxwell equations we now use with this nablas and vector products, that was invented by Heaviside. The vector notation was independently discovered in the United States or developed in the United States by the mathematician named Joshua Willard Gibbs, who was the first professor of theoretical physics in the United States in the Yale University. But the application was a Heaviside. Heaviside was also the man who invented what is called operation calculus, a method of solving ordinary differential equations by a symbolic way, by solving linear algebraic equations. And that was a mathematical step which was considered at that time by mathematicians to be completely ridiculous. And that is why he said that mathematics is an experimental science, and that definitions, because nowadays we know that the operation calculus invented by Heaviside is nothing else than the Laplace transform in mathematics. So everything was known, but he just employed it. He was supporting himself by writing short stories for a journal for electricians. There was a kind of an industrial journal called Electrician in England in the 19th century, and Heaviside was writing short stories for the journal and was supporting himself. There's a complicated story with him. So anyway, the Heaviside was a man, and he is actually the first person who used a telegraph equation, which we discussed before, to describe the properties of electric transmission lines. So let's discuss the transmission line. This is a transmission line, a kind of a real, how it looks really, and on the right-hand side we have a mathematical model for it. The transmission line, there's a wire, a central wire, there is a surrounding wire, and the area in between is filled up with the material which has a certain dielectric constant epsilon. And since this wire is seldomly used without being connected to something, there is no net electric charge transfer through each of the ends, and therefore if there is electric current going through the center of the wire, there must be electric current which goes in the opposite direction over the outer layer, and the charge density per unit surface of that outer layer I will call the capital Q. And the inner radius of the wire is Ri, and the outer radius is R with sub O. And the length of the wire I will denote it as by letter Z. Okay, so that is our construction. So as we remember from the, I believe, first lecture, the magnetic field generated by the current which goes via the center wire is proportional to the current I, and it's inversely proportional to the radius. So I now can calculate the magnetic flux, which is an area integral of the magnetic flux vector B, and the calculation is very simple, and we find out that the flux has this queued logarithmic connection. And since this is a logarithmic connection, then I can calculate easily the impedance, which is a flux divided by the current, and I calculate the impedance per unit length. That is why I have divided it also by the distance z. So the impedance per unit, this unit length of that wire is given by the formula, and it is measured, as we remember, in henries per meter.
And this equation is only for vacuum coaxial line. If you have
there's a because if this is not a ferromagnetic material, then the magnetic mu is equal always to mu0.
No, magnetic, well, but epsilon is if it is not 1.
Yeah, but there's no maximum, there's no magnet so far. It will show up in a moment. The epsilon shows up in the electric field, not in the magnetic.
But you said that you calculated impedance, and that will be
the L, on the impedance, not the complex impedance. I calculate the real part of it. So that is just the flux divided by the current. And Z is not the, no, it's not the impedance, it's the length. That is confusion. But now I can calculate, because if there is a current density per unit area on the outer layer of the current, then there is an electric field inside of the wire, and that electric field is resulting in a voltage, which I can also calculate, and the voltage is the proportion to the Q and also to this same logarithm. And that allows me to calculate the capacity of the wire, which is the charge divided by the voltage, and that turns out to be the capacitance of the wire, and it's measured in volts per meter. So if I have this wire, I have calculated the impedance per unit length, and I have calculated the capacity per unit length. And why I did it? Because if I have that wire, then that was the great idea of Mr. Heaviside, then I can describe that situation, replace my complicated wire by the very simple model of a circuit. The circuit which consists of the impedance and parallel connected capacitors. So the whole theory of the wire can be envisaged as the analysis of the circuits which I had written here. And that kind of a circuit is easily analyzed mathematically because I can now make a continuum model of it. So I have no coils connected to each other, but I had a certain distance dz, which has impedance per unit length L. And the same piece of the wire, of my coaxial wire or my transmission line, has a capacity C per unit length, dz. So I have now the following mathematical object to describe. I have a slab which has a thickness dz, which is characterized by the impedance capacitance C, and in a second also resistivity, if I will add it. And there is applied voltage to it and coming current. So there's a voltage V and the current I from the left, and some slightly larger voltage and slightly larger current on the right. And of course the same happens by a symmetry, as we discussed. If this is a current going through the center of the wire, there must be the current going in the outer layer backwards. So I have the similar situation that if the current goes to the left, then it must be slightly smaller on the right. Okay, so now let's do some algebra. Let's calculate the change in the current, the delta. That is, of course, a derivative of a current with respect to the distance z times the thickness of our slab. And from where this electric current may come? Well, it comes from the capacitor. So the delta E is proportional to the capacitance C times the derivative of the voltage. So we have a first equation that we have calculated the change of the electric current in our model of a wire, and that is given by that equation. So if I get rid of this finite difference notation, then I have obtained the differential equation that the derivative of a current with respect to z is proportional to the derivative of the voltage, and is proportional to the capacitance per unit length. So let's now calculate the change of the voltage. The change of the voltage is the same derivative of the voltage, and the voltage change is proportional to the impedance, to the time derivative of the current. So I have this other equation that the derivative of a voltage with respect to the z is proportional to the impedance times the time derivative of the current. So I have two equations, the derivative of a current and with respect to z, and derivative of the voltage. And that is now a pretty trivial operation. Let's take the first equation. Let's take the equation for the voltage. We have a first derivative of a voltage with respect to z, and let me calculate now the second derivative of that voltage, but now with respect to the time. Then on the right-hand side, I will get the second derivative of the current with respect to time. And then I do the same operation with the equation for the current. Calculate the time derivative of a first derivative of a current with respect to z. And then on the right-hand side, I will have the second derivative of time of a voltage. Well, because the second derivatives must be equal, then I will obtain, from those two, one equation for a voltage, which is the D'Alembert equation. I obtain the wave equation for a voltage in our transmission line, and the coefficient is called 1 over LC, and from the dimension analysis, because the distance is the velocity times time, then we see that the wave, which is described by the equation, propagates with the velocity, which is 1 over the square root of the impedance times the capacitance. So that is the wave equation, and that means that the problem of describing the transmission line is, by a beauty of the Maxwell equation, reduced to the solution of the wave equation. Well, but in nature, there is also resistivity. And this transmission line is not built out of the ideal material which doesn't have a resistivity. So it has connected not only impedances, but also the resistivity. So I have to repeat now my calculation with the same slab, but that slab, in addition to the impedance, conductivity, capacitance, will also have the resistivity. And if I do this, then my equation will be that equation which contains not only the second derivative of voltage with respect to time, but also the first derivative. So this is our equation which we already have seen at the beginning, and this is a telegraph equation. And that is the equation which...
I have a question.
Yes?
What is the physical significance of
is correct.
Sorry?
Of course, the C will be always there because the electric current comes from the change of voltage in time. So it comes from the capacitor. So everything is fine. Unit-wise as well. So this is a correct equation.
No, I am not asking you about correct.
Yeah.
Physical significance. What is the properties of that?
So what you are asking for?
Actually, I am asking what is the physical significance that why we put that term here?
Because this outer layer and inner layer, they have a conductivity.
Okay.
They are made out of the metal and they are not ideal. So the conductivity is not infinite. So it has a certain resistivity.
So you have dissipation.
You have we will see in a moment. The wave equation is a signal propagates with the same velocity through all the medium. But if there is a resistivity, then there is this first derivative, so it will have a certain decay, will have a certain length over which decay, and this is how is dissipation.
So RC is characteristic time constant
of the
discharging a capacitor through a resistor. So
we will come to this in a moment, but that is the equation. And this is what is called the telegraph equation, and that was it's written in a form which was derived by the Oliver Heaviside. And that mathematical equation is the fundamental equation for describing the transmission line. So let's study first the case where there is no dissipation. Then we have only the wave equation. And the important thing is that we have this equation for transmission line, and we will see in the next lecture that it is precisely the same equation which we need to describe the waveguides. And then we will see that this is precisely the same equation we need to describe the optical fibers. So this is a one-dimensional wave equation, and this equation was solved first time by Riemann, who observed that the solution of that equation is having a very strange properties, namely, if we have two arbitrary functions, f and g, completely arbitrary, then the general solution of the wave equation in one dimension is a combination of a one function which depends on z minus vt, and the other functions which I call g, which depends on z plus vt. So if I sit in the coordinate system in which moves with the velocity v, then f function describes the wave going in the one direction, and the g function describes the function which moves in the opposite direction. So in the thing is that I can call these two functions multiplied as a v plus and v minus, a voltage going right and a voltage going left on my picture. So let's recall our first equation, that the z derivative of electric current is proportional to the time derivative of voltage. And if we use my notation, we can easily find out that the electric current which goes into the wire is proportional to the difference of those two voltages with a certain coefficient. And this coefficient is what we call complex impedance, and which is in this dissipation-less model is just the square root of impedance divided by the capacitance. So we have solved the wave equation, and now let's discuss the final thing for this today. Namely, we have that wire, and we connect it to whatever. We load it, we connect it to some device or anything else. So now we have the following picture. Our fictitious circuit, which describes our transmission line connected to the load, is our transmission line, which is connected to the object which has some kind of a load, which I called Z sub L. All right, so that explains the notation. The complex impedance of the line is Z0. The impedance of the load is called ZL, and I can calculate now the circuits. And again, I have a voltage on the load, which is a sum of the voltages, and the current through the load, which is a sum of those two currents. And this is some very simple algebra which produces the formula I have here, that the voltage of the load divided by the complex impedance of the load is given by this simple formula. And I can solve it, and I can define the quantity which is called the reflection coefficient. And this is a ratio of the, because the V plus goes right, so it is convenient to say that I am looking of what is going left as going left as the reflection. So I calculate the ratio of the voltage going left divided by the voltage going right, and this ratio is what usually quite intuitively we will call a reflection coefficient, and that the reflection coefficient is completely described as in terms of the impedances. So this is impedance of a load minus the impedance of the wire divided by the sum of those impedances. So that is the reflectivity coefficient. And
it has a lot of practical
yes,
consequences.
we will. And then it, of course, means that I can also define what is called the transmission coefficient, which is the ratio of the carrying voltage to the voltage in the load. And this is called the transmission coefficient. Now it is very easy to look up at it, that if we have the system where the impedance of the network is very, very small as compared to the complex impedance of the load, then the reflection coefficient is essentially 1. Because we can, the numerator and denominator, they cancel. And if the load is much lower than the load, the impedance of the load is much lower than the impedance of the network, then the reflection coefficient is equal to the -1. And this is the mathematical base of a method of finding out how good is my wire. I send the wave through it, and I measure the reflection coefficient and transmission reflection coefficient, and by putting a very heavy load at the end of it, I can see whether my wire is really good or not. So that is what it happens. Okay? So let's look up at what happens when we apply the voltage, and we apply the voltage which changes in space as a wave, with the wave vector k. Then I can calculate that the voltage at the point Z is proportion. It has a part which is just a plane wave, and a part which is proportional to the reflection, and which goes into opposite direction. So that allows me to calculate the quantity which is of a tremendous use by the radio engineer, which is called voltage standing wave ratio, which is the ratio of the reflectivity coefficient given here, which allows me to turn the cat upside down and calculate the module of R in terms of this coefficient, which is, how should I pronounce it? Voltage standing wave ratio. So that is basically what I would like to tell about the transmission line. And the important thing is that the equation described the properties of the wire is the wave equation for if there is no resistivity, and the telegraph equation when there is a dissipation. So actually what moves over the electric wire connecting power plant and our home is not electrons. It's the wave which propagates in a thin layer of the wire, which pushes some electrons slightly this direction, then backwards and backwards, and what eventually heats up the heater is the very little of the electrons which sits in that wire. What operates in the heater when you turn it on, it's not the electrons which are sent from the power plant, but the electrons which are already in the heater. So next time we were going to talk about waveguides, which is even more fascinating, and it will require some more mathematics. Thanks. Any questions?